All right, it's recording.
Okay, thank you. All right, so welcome back. Interlude. So, final third of the course, pushing forward on magnetism. So we're going to talk today about forces on moving charges in magnetic fields. We already started this a week ago, last Tuesday, with the expression that's on the chalkboard behind me. So we're pretty much going to focus on that for the entirety of this morning. No in-class problems today, but we'll do some on Thursday. So let me just outline what we will cover. Start off with this. Explore some of the types of motions that might be of interest. Since we now know about forces on charges in magnetic fields, and of course earlier in the semester we know about forces on charges in electric fields, it's natural to combine them, so we'll do that. We'll look at, in particular, motion of moving charges in uniform magnetic fields, and gives rise to a certain type of motion, which you know well, so we'll explore that a little bit more. And then we'll kind of recast this expression, not just in terms of charge and velocity, but we'll kind of merge these two variables together and actually express it in terms of the current and the current carrying wire, so the same physics, but slightly more macroscopic perspective. We'll take that wire, bend it into a loop, and see what happens there. And then lastly, we'll talk about how a current carrying loop can be viewed as a magnetic dipole. So lots of similarities with things we covered in electrostatics, with electric fields. In most cases, there are interesting twists when it comes to magnetism, in part because of the increased complexity of the force law for charges in magnetic fields. Just one comment for those of you who are following the textbook relatively closely. This is roughly chapter 27. You'll find in the textbook Gauss's law for magnetic poles, magnetic fields, in this section of the textbook. I'm not going to put it in lecture today. It's going to come back in a couple of sessions from now. But don't overlook it. When you're looking at the textbook, Gauss's law for magnetism is something you should know, and it'll become relevant as we get towards the end of the semester. Okay, so let me remind you where we were a week ago. Force on a moving charge in a magnetic field. So here's the new expression, and it has two features that are new compared to what we saw with electric fields. Firstly, the appearance of a velocity term. We have no magnetic force unless the charge is moving. So this is obviously a big deal. And then the other thing that is quite new is the directional aspect of this, which invokes the right-hand rule, of course. And so our force on our moving charge is now perpendicular to both the velocity and to the magnetic field, okay? So I'm not going to spend any time refreshing you on the right-hand rule. We did that in the first semester. I'll repost notes in what I post online just for a refresher for you, but it's essential that you know how to use the right-hand rule for the rest of the semester. It absolutely is critical for everything to do with magnetism, okay? All right, so that's the recap of where we finished last time. And of course, I can express this now, vector product, cross product, in terms of what's written below. So here it is in magnitude form, charge times the magnitude of the velocity times the magnitude of the B field, multiplied by the sine of the angle between the velocity and B field vectors, okay? So in some cases, and particularly what we'll discuss in a few minutes, these are actually perpendicular. That simplifies things a little bit. We have 90 degrees between the two of these things. So the sine of that angle is 1. So the magnitude of the force when these are perpendicular is just Q times V times B. Okay? But more generally, it's going to be with the sine phi angle in that. Yeah, good.
Is the units of the the same as in the field?
Okay, good question. We're about to address it. Just to repeat the question and then just have you think about something before I answer it. So if you look at this and compare it, we kind of had a compare and contrast exercise last Tuesday. Of course, the variables are somewhat different here than they were for the electric field. So just knowing that, do you expect the units for B field to be the same or different than those for E field? If you want to wait, that's fine too. Okay, hold on. So how might we figure out what the units for B are? Well, let's take a look. So in a sense, if you remember what we did previously for, actually let me try and start making this a little bit more distinct. Now we're talking about the force due to a magnetic field. If you remember from a few weeks back, we had a force due to an electric field, looks like this, okay? And so what we did was basically take this and maybe in a sense kind of use it as a way to define units for, in this case, the electric field. This. So you can figure out what the units for electric field are for this. Force, newtons in SI units, charge, coulombs in SI units. So electric field units, newtons per coulomb. Okay. So I could do a similar thing here. Let me take this version of it to ignore the complexity coming from the vector product. So I could say in this case, and I'm just worrying about magnitude now, that B equals the magnitude of FB over Q times V, and then there's something which is the sine of an angle. Obviously that has no dimensions. So this would allow us similarly to figure out what the units for magnetic field are. So force, again, newtons in SI units. Down below, I still have charge, so everything up until this point is the same, but of course I knocked up. So now I have velocity, which is presumably meters per second in the denominator, and then sine of an angle, which is dimensionless, okay? So this tells you the answer. This tells us now what the units are for magnetic field. So newtons over coulomb meter, and with this being in the denominator, I can put this up in the numerator, and we get some reasonably complicated unit, okay? Now, as always, when we get some reasonably complicated unit like this, our natural tendency is to redefine it as something, and so we're actually going to do just that. And we are going to redefine this as the Tesla. Okay, in SI units, magnetic field is now measured in Tesla. But if you're ever struggling to remember what the units are, just go back and do this exercise so that you can reconstruct it in more fundamental units. But we're going to work in Tesla. Okay? So, this is our SI unit for magnetic field. Let's see. I tried to give you a few weeks back a sort of sense of scale for electric fields or sort of common types of situations, so it's not a bad idea to do something similar for magnetic fields. Where have we experienced magnetic fields? Well, the Earth's magnetic field would be one of this case. Anyone happen to know order of magnitude, ballpark, Earth's magnetic field? And I've talked about Tesla so far, so people know some other types of units for magnetic field. This could be some guess or knowledge of what Earth's magnetic field is. Yep.
10 to the negative 4 Teslas.
Okay, pretty good. Okay, so the Earth's magnetic field is indeed around 10 to the minus 4 Tesla. And I mentioned there are other types of units. I will try and steer clear from these because I much prefer to stick with SI units, but there is another parallel unit of magnetic field called the Gauss, which turns out to be in fact 10 to the minus 4 Tesla. So in fact the Earth's magnetic field is about 1 Gauss. Okay. You saw me play around with a bar magnet last week, so
I was going to ask, like, how big is a Tesla in terms of like physical magnetic power? Is it like the case with like a capacitor where like 1 farad is like pretty huge, or is it like
yeah, so 1 farad in terms of capacitance we saw is pretty big for practical devices. I'm trying to give you a little bit more of a sense of this. The Earth's magnetic field, you already have a sense of relative strength here. You saw me play around last Tuesday. I don't have something to repeat it with now. You saw me play around with a bar magnet and a compass needle, right? So So a compass needle, when it's not near any other magnets, it's purely sensing the Earth's magnetic field. It's going to align in a certain way, but you can tell from looking how a compass moves, it's not a particularly strong force in terms of daily forces. I take my bar magnet and I can easily override the Earth's magnetic field with this. And so it tells me that in fact near one of these poles, the magnetic strength is probably 10 to the minus 2, 10 to the minus 1 Tesla, something like that, probably 10 to the minus 2. So let me say for a bar magnet, and these are all just rough estimates, it's maybe around 10 to the minus 2, something like this. So a Tesla, yes, in this sense, is starting to get pretty strong. So the next sort of common context where I often give examples, and these are things that are less common in daily life, but many of you will have experienced them. Let me ask you, where have you maybe come into contact with stronger magnetic fields? Contact. MRI. What's an MRI? Magnetic resonance imaging system. Okay, so obviously something used in medicine, diagnostic, and indeed MRI machines, these are electromagnets, right? So they're powered by currents moving through the machine in a way that we'll explore this morning. Indeed, they're pretty strong magnetic fields. They're typically of order of Tesla or so. These days, maybe a couple of Tesla. Let me do an order of magnitude. It's around 1 Tesla, something like this. And they're pretty strong. There are, as you will be learning in the next couple of weeks, good reasons why you are very carefully screened for what you have in your body or in your clothing or wearing on your skin before you go in an MRI machine, because if there are metallic elements inside an MRI machine, bad things can happen. Okay? So this is starting to give us a sense of scale. So yes, a Tesla in terms of daily experience is pretty big. Okay? In terms of the most powerful electromagnets that we have available to us these days, let me call this E-Max for electromagnets made by people, probably about 100 Tesla. It's already big enough, and again we'll explore more about this through today's class, that forces on moving charges in magnetic fields of this strength are enormously strong. And in fact, the electromagnets that are built with this sort of magnetic field strength are usually so powerful that when you energize them, the forces on them are so big that they basically self-destruct. So they're one-time gadgets, they blow up when you do this. Okay? And to, as always, set the scale that we live in a universe that's way more exotic than just what we have here on Earth. Some of you are aware of things called neutron stars. Magnetic field strengths at the surface of neutron stars are calculated to be around 100 million Tesla. Okay, so they're pretty powerful magnets. So that gives you a sense of scales of magnetic field. Okay, so with that said, I'm going to skip a few things that are going to be in this chapter in your textbook simply because they're relatively straightforward and best sort of absorbed just by one-time reading. Let me now, we've explored a little bit about the force on moving charges in magnetic fields. Let me go back and reincorporate the possibility that we have not just a magnetic field but also an electric field. So now it's force on a moving, well maybe a charge in E and fields. Okay, so we have the necessary ingredients to figure this out on the board on the left-hand side. So now I have a charge moving in both an electric and magnetic field. So no big surprise, all I need to do is combine these two things in a nice compact mathematical form. And that's what we get. Okay? So now we have the possibility of forces coming from both an electric field and a magnetic field. So don't be worried in any sense by the sort of slight increase in complexity here. As with anything in physics, superposition helps make our life easier. And so here we've got a force component that's in the direction of the electric field. Here we've got a force component that's perpendicular to the directions of both of these things. So you can look at this in terms of two sub-forces, if you will, add them together by superposition and figure out what the net force is. One thing I will emphasize again, which I haven't said yet this morning, but I probably should emphasize several more times, is the way this is set up is it's set up assuming we're dealing with a positive charge, okay? So this right-hand rule setup is assuming a positive charge, and of course if it's a negative charge, then we simply change the direction of our force, okay? So all fairly straightforward stuff, I would say. Okay, so that's the basics in terms of force on charge. We're going to turn our attention for the next little while just to a magnetic field again. Maybe I'll say this so I don't forget as we go further into lecture. There are at least 2 or 3 examples of practical applications of this expression on the board behind me. I'd like you to read through them. I'm not going to cover them in class for the same reason. It's sort of more efficient use of your time just to read them on your own time. But let me just say a couple of scenarios that are interesting. One is related to this device, which I'll show you in a little while. And it has to do with making use of both electric and magnetic forces on moving charges to figure out something fundamental about the charges themselves, okay? So that sounds a little bit cryptic. To be more specific, knowing this allowed scientists about 120, 130 years ago to measure for the first time fundamental properties of electrons, okay? We'll talk a little bit more about that when I show you this gadget. The second important example I'd like you to read is something called the Hall effect. And this has to do with charges flowing through macroscopic chunks of material in magnetic fields. And it turns out that the combined forces due to magnetic forces and due to electric forces, and you'll have to read exactly how this happens, can again be used to allow us to figure out something fundamental about charge is in those materials. Most usefully, it allows us to figure out something about the density of charge carriers in those materials, okay? So please make sure to read that section on the Hall effect. It's a super useful phenomenon in sort of condensed matter physics. Okay, so let me come back to this and have you tell me what type of motion you would now expect. We're going to, for much of the rest of this morning, talk about magnetic fields that are uniform, so they're constant everywhere in space. What I'd like you to do is imagine that I have now a positive charge down at the bottom here, moving from left to right, and it's moving in an environment of a uniform magnetic field, which in this case is into the plane of the board. Okay? So, take a look at what's on these 2 boards, and tell me what you predict to be the motion of that charged object.
So you'll move through a straight path and the force will act upward and be through this.
Okay, good. So, to paraphrase Elizabeth's answer, it will be circular. Indeed, it will. Okay, so why? And we'll be illustrating here something that's characteristic of forces due to magnetic fields. So first off, let's take our right-hand rule. Velocity of a positive moving charge, left to right. That's my forefinger, middle finger, this configuration into the plane of the board. My thumb gives me the direction of the magnetic force on this object. So it's experiencing, let me add this in maybe some color. It's experiencing a force that is perpendicular to its instantaneous velocity. We know that's true. We already learned this right at the get-go over here. So it's perpendicular to the instantaneous velocity. That means, if you think about it, a charge moving in a magnetic field will never change its speed, but it will change its velocity. Okay, let me say that phrase again. It will never change its speed, speed doesn't change, the magnitude of the velocity doesn't change, but the direction does. Okay? So imagine this is what happens. It gives it a little kick, which in this case is upwards. So presumably after it's received that kick, the velocity is shifted a little bit so that it's this sort of. Do the same exercise again. Your right-hand rule will tell you that there's still a force that's perpendicular to its velocity, and it's kind of in that direction. So what you're seeing, if you look both at the magnitude and the direction of this force, is that it has a constant velocity, and it's always perpendicular to the instantaneous direction of the velocity. So of course this is mapping out the conditions we need for uniform circular motion. And of course we explored this in first semester in mechanics. And so this thing is indeed, okay, I'm giving enough space here to do it really fully. But if the magnetic field is uniform, this will map out a circular path. And that turns out to be the basis of lots of super useful practical applications. So let me show you a couple of demonstrations now. I'm going to lower the light level. Can I do this? Okay, so I think Saul asked me what this is. What is this?
Cathode ray tube.
Yes, it's a cathode ray tube. What is a cathode ray tube? A TV screen. Yeah, it kind of is a TV screen. Michael?
Shoots a bunch of electrons, and basically uses magnets to shoot where the electric
Yep. And it looks like Noah's been scrutinizing Google to find out what the answer is.
No, I just had a fun fact. So, like,
Okay, fun fact.
an old-timey name for an electron is a corpuscle.
That's correct.
Yeah.
Okay, thank you for that piece of information. Okay, this used to be what TVs looked like. Okay, you guys are young enough that you've never really seen these things. But indeed, this is what the TV tube used to look like from the side. Back here is an electron gun. Okay, quite how we produce electrons is not particularly important, but basically we just heat a chunk of metal. Electrons fly off. We put them in an environment where there's an electric field, so they're accelerated towards a positive potential. Okay? So, electrons streaming off this hot cathode, they're accelerated towards a positive potential anode. We gain speed. We put a baffle there with a little hole in the middle, and it blocks all of the electrons except those that are just traveling through this hole, so we get a collimated beam of electrons. That's what's happening at this end. Over here, we have a space that's somewhat empty. In fact, it's vacuumed to some extent. And then on the front end, we have a screen. That screen is coated with a material such that when electrons hit it, they give it energy, because they've got kinetic energy. But it's coated in a material that, once it's excited by electrons hitting it, the extra energy that's given to that material is emitted in the form of light. Okay? So if I turn this thing on, hopefully something appears after a couple of seconds. Anything appearing? No? Okay. Still nothing?
Oh, yes.
Okay, what do you see? See light? Okay. So you probably see a dot, right? So that is where that collimated electron beam is hitting the screen. So if it's the screen, its energy is given up to molecules, atoms in this coating, and then as the energy is released, it gives out light. All right, so inside this piece of it, and this is exactly how your old-fashioned cathode ray tubes TVs used to work, we can apply both electric and magnetic fields in a direction that's perpendicular to the velocity of the electron beam. And of course, as you now see on here, there are going to be forces acting on those moving charges represented by the weight behind you. So this can be set up in a very sophisticated way so that we take signals from whatever, typically electronic circuits, so on and so forth, and we can use those signals and apply them to vary the electric fields across this traveling electron beam, or if we apply them to electromagnets, we can actually set up magnetic fields as well. So, complicated device, but in the case of a TV screen, what we would have done in the old-fashioned TVs is basically raster this beam back and forth many hundreds of times a second across the complete screen, and we would encode information based on the electronic or electrical signals we feed into the electric and magnetic fields to vary the strength of the field as it rasters across the screen. And that used to be how you would produce TV pictures. So it's been cut away, and the simple way to show one effect of magnetic fields on moving charges now is simply to take this and kind of pretend I'm putting a magnetic field across this, but now in a less controlled way. I'm just going to take this and stick it near the electron beam where it comes out. And probably you'll see it move. Okay? No? No? Okay. So the electron. Okay, so charge is moving this direction. I've got my bar magnet here. Roughly speaking, it's got magnetic field lines coming out in that sort of dipole shape that we explored a week ago. But to some extent, the magnetic field is horizontal here. So what I'm expecting, without having seen this, is that the bright spot moves vertically up and down. Okay? Is it going vertically up and down? Okay. If I put it here, it's going to move horizontally side to side. Okay? So, a little bit, thank you. Let's see what happens now if I take a similar charge beam, but I put it in a uniform magnetic field in this orientation. That's what this gadget's all about. So, turn this off, let's give it away. You saw this as we started out. It's going to be dark for a moment, okay? Don't be alarmed. Okay, so you can clap. So now I have an electron beam which is being fired from the bottom of this device. It's again vacuum more or less inside, but it has a trace amount of certain types of, actually I kind of feel it's mercury vapor, but I'm not certain. Same phenomenon. The electron beam hits the molecules, it excites them, the molecules release their additional energy by emitting light. This is now in a uniform magnetic field, which is in a direction either towards or away from me, from your perspective. And so now you're seeing this motion roughly in uniform circular motion, okay? And if I vary the strength of the magnetic field, I should be able to vary the radius of curvature of this. Okay, so very fun. Let's see if I can find the lights without falling over things. Okay, so now we've got uniform circular motion of charges moving in constant magnetic fields. Let's look at it a little bit quantitatively. This turns out to be the basis of lots of useful things, particularly in fundamental physics. Things like particle accelerators and everything that goes into fundamental particle physics relies a lot on this. Okay, so uniform circular motion in constant E field. So you already told me what the motion is there. Let's be quantitative now. What is the magnitude of the force? Well, it's perpendicular to the B field, perpendicular to the velocity. So the magnitude of the force is just Q times V times B. And again, I've set up V and B to be perpendicular, so the sine of the angle between them is 1, which is why we don't see explicitly vector product in here anymore. So this is the magnitude of the force, and of course, since it's now, as we've learned, uniform circular motion, I expect the same expression we had from the first semester in Newtonian mechanics, where I can say the force is also the mass times the centripetal acceleration. Okay? So now we've got a reappearance of uniform circular motion where the force comes now from this rather than from some, let's say, mechanical levers. All right, so if we've got this, we can simply rearrange it to find the radius of curvature here. And what we find is this. So the radius of that green beam that you were seeing a few moments ago is determined in terms of these parameters. Okay? Mass of the electron in this case, magnitude of the charge on the electron, the velocity with which we're firing them out of our